Hi, this is the first lecture in MIT's course 1806, Linear Algebra, and I'm Gilbert Strang. The text for the course is this book, Introduction to Linear Algebra, and the course webpage, which has got a lot of exercises from the past, MATLAB codes, the syllabus for the course is web.mit.edu/18.06. And this is the first lecture, lecture 1. So, and later we'll say which will give the web address for viewing these videotapes. Okay, so what's in the first lecture? This is my plan. The fundamental problem of linear algebra, which is to solve a system of linear equations. So let's start with the case when we have some number of equations, say n equations and n unknowns. So an equal number of equations and unknowns. That's the normal, nice case. And what I want to do is, with examples, of course, to describe first what I call the row picture. That's the picture of one equation at a time. It's the picture you've seen before in 2x2 equations where lines meet. So in a minute, you'll see lines meeting. The second picture, I put a star beside that, because that's such an important one, and maybe new to you, is the picture a column at a time. And those are the rows and columns of a matrix. So the algebra way to look at the problem is the matrix form in using a matrix that I'll call A. Okay, so can I do an example? The whole semester will be examples, and then see what's going on with the example. So take an example. 2 equations, 2 unknowns. So let me take 2x minus y equals 0, let's say, and minus x plus, say, 2y equals 3. Okay. I can even say right away, what's the matrix what's the coefficient matrix? The matrix that involves these numbers. A matrix is just a rectangular array of numbers. Here it's 2 rows and 2 columns. So 2 and minus 1 in the first row, minus 1 and 2 in the second row. That's the matrix. And the unknown, well, we've got 2 unknowns. So we've got a vector, x with 2 components, x and y. And we've got 2 right-hand sides that go into a vector 0, 3. I couldn't resist writing the matrix form even before the pictures. So I always will think of this as the matrix A, the matrix of coefficients. Then there's a vector of unknowns. Here we've only got 2 unknowns. Later we'll have any number of unknowns. And that vector of unknowns, well, I'll make that x extra bold. And the right-hand side is also a vector that I'll always call B. So linear equations are AX equal B, and the idea now is to solve this particular example and then step back to see the bigger picture. Okay, what's the picture for this example? The row picture. Okay, so here comes the row picture. So that means I take one row at a time, and I'm drawing here the xy plane, and I'm going to plot all the points that satisfy that first equation. So I'm looking at all the points that satisfy 2x minus y equals 0. It's often good to start with which point on the horizontal line. On this horizontal line, y is 0. The x-axis has y is 0, and that, in this case, actually, then x is 0. So the point, the origin, the point with coordinates 0, 0, is on the line. It solves that equation. Okay, tell me, well, I guess I have to tell you, another point that solves this same equation. Let me suppose x is 1, so I'll take x to be 1. Then y should be 2, right? So there's the point 1, 2 that also solves this equation. And I could put in more points. But let me put in all the points at once, because they all lie on a straight line. This is a linear equation, and that word linear got the letters for line in it. That's the equation. This is the line of solutions to 2x minus y equals 0, my first row, first equation. So typically maybe x equal a half, y equal 1 will work. And sure enough, it does. Okay, that's the first one. Now the second one is not going to go through the origin. It's always important. Do we go through the origin or not? In this case, yes, because there's a 0 over there. In this case, we don't go through the origin because if x and y are 0, we don't get 3. So let me again say, suppose y is 0. What x do we actually get? If y is 0, then I get x is minus 3. So if y is 0, I go along minus 3. So there's one point on this second line. Now let me say, well, suppose x is minus 1. Just to take another x. If x is minus 1, then this is a 1. And I think y should be a 1. Because if x is minus 1, then I think y should be a 1, and we'll get that point. Is that right? If x is minus 1, that's a 1. If y is a 1, that's a 2, and the 1 and the 2 make 3, and that point's on the equation. Okay, now I should just draw the line, right? Connecting those 2 points, that will give me the whole line. And if I've done this reasonably well, I think it's going to happen to go through, well, not happen, it was arranged to go through that point. So I think that the second line is this one, and this is the all-important point that lies on both lines. Shall we just check that that point, which is the point x equal 1 and y was 2, right? That's the point there, and that, I believe, solves both equations. Let's just check this. If x is 1, I have a minus 1 plus 4 equals 3. Okay. Apologies for drawing this picture that you've seen before. But seeing the row picture, first of all, for n equal 2, 2 equations and 2 unknowns, it's the right place to start. Okay, so we've got the solution, the point that lies on both lines. Now can I come to the column picture? Pay attention. This is the key point. So the column picture. I'm now going to look at the columns of the matrix. I'm going to look at this part and this part. I'm going to say that the x part is really, is really x times, you see I'm putting the two, I'm kind of getting the two equations at once. That part, and then I have a y, and in the first equation it's multiplying a minus 1, and in the second equation a 2, and on the right-hand side, 0 and 3. You see the columns of the matrix? The columns of A are here, and the right-hand side B is there. And now what is the equation asking for? It's asking us to find, somehow to combine that vector and this one in the right amounts to get that one. It's asking us to find the right linear combination. This is called a linear combination. And it's the most fundamental operation in the whole course. It's a linear combination of the columns. That's what we're seeing on the left side. Again, I don't want to write down a big definition. You can see what it is. There's column 1, there's column 2. I multiply by some numbers, and I add. That's a combination, a linear combination, and I want to make those numbers the right numbers to produce 0, 3. Okay. Now I want to draw a picture that represents what this is algebra. What's the geometry? What's the picture that goes with it? Okay. So again, these vectors have 2 components, so I better draw a picture like that. So can I put down these columns? I'll draw these columns as they are, and then I'll do a combination of them. So the first column is over 2 and down 1, right? So there's the first column. The first column, column 1. It's the vector 2 minus 1. The second column is, let's see, I go over minus 1 is the first component and up 2. It's here. There's column 2. So this, again, you see what its components are. Its components are minus 1, 2. Good. That's this guy. Now, now I have to take a combination. What combination shall I take? Why not the right combination? What the hell? Okay. So the combination I'm going to take is the right one to produce 0, 3, and then we'll see it happen in the picture. So the right combination is to take x as one of those and 2 of these. It's because we already know that that's the right x and y, so why not take the correct combination here and see it happen? Okay, so how do I picture this linear combination? So I start with this vector. That's already here. So that's 1 of column 1. That's 1 times column 1, right there. And now I want to add on. So I'm going to hook the next vector on to the front of the arrow. We'll start the next vector, and it'll go this way. So let's see. Can I do it right? If I added on one of these vectors, it would go left 1 and up 2. So it would go left 1 and up 2, so it would probably get us to there. Maybe I'll do dotted line for that. Okay? That's 1 of column 2 tucked on to the end, but I wanted to tuck on 2 of column 2. So that the second one will go up left 1 and up 2 also. It'll probably end there. And there's another one. So what I've put in here is 2 of column 2 added on. And where did I end up? What are the coordinates of this result? What do I get when I take 1 of this plus 2 of that? I do get that, of course. There it is. There it is. X is 0, y is 3. That's B. That's the answer we wanted. And how do I do it? You see, I do it just like the first component. I have a 2 and a minus 2. That produces a 0. And in the second component, I have a minus 1 and a 4. They combine to give the 3. But look at this picture. So here's our key picture. I combine this column and this column to get, maybe I better, to get this guy. That was the B. That's the 0, 3. Okay. So that idea of linear combinations is crucial. And also, do we want to think about this question? Sure, why not? What are all the combinations? If I took, can I go back to x's and y's? This is a question for really, it's going to come up over and over, but why don't we see it once now? If I took all the x's and all the y's, all the combinations, what would be all the results? And actually, the result would be that I could get any right-hand side at all. The combinations of this and this would fill the whole plane. You can tuck that away. We'll explore it further. But this idea of what linear combination gives B, and what do all the linear combinations give? What are all the possible achievable right-hand sides B? That's going to be basic. Okay, can I move to 3 equations and 3 unknowns? Because it's easy to picture the 2-by-2 case. Let me do a 3-by-3 example. Okay, I'll sort of start it the same way, say maybe 2x minus y, and maybe I'll take no z's as a 0, and maybe a minus x and a 2y, and maybe a minus z is a, let me make that a minus 1. And just for variety, let me take minus 3z, minus 3 y's. I should keep the y's in that line. And 4 z's is, say, 4. Okay. That's 3 equations. I'm in 3 dimensions, x, y, z. And I don't have a solution yet. So I want to understand the equations and then solve them. Okay. So how do you understand them? The row picture is one way. The column picture is another very important way. Just let's remember the matrix form here, because that's easy. The matrix form, what's our matrix A? Our matrix A is this right-hand side, the 2 and the minus 1 and the 0 from the first row, the minus 1 and the 2 and the minus 1 from the second row, the 0, the minus 3, and the 4 from the third row. So it's a 3-by-3 matrix. 3 equations, 3 unknowns. And what's our right-hand side? Of course, it's the vector 0, minus 1, 4. Okay. So that's the way, that's the shorthand to write out the 3 equations. But it's the picture that I'm looking for today. Okay. So the row picture. All right, so I'm in 3 dimensions, x, y, and z. And I want to take those equations one at a time and make a picture of all the points that satisfy. Let's take equation number 2. If I make a picture of all the points that satisfy, all the x, y, z points that solve this equation, well, first of all, the origin is not one of them. X, y, z being 0, 0, 0 would not solve that equation. So what are some points that do solve the equation? Let's see, maybe if x is 1, y and z could be 0. That would work, right? So there's one point. I'm looking at this second equation here just to start with. Let's see. Also, I guess if z could be 1, x and y could be 0, so that would just go straight up that axis. And probably I want a third point here. Let me take x to be 0. Let's say x to be 0, z to be 0. Then y would be minus a half, right? So there's a third point. Somewhere, okay. Let's see. I want to put in all the points that satisfy that equation. Do you know what that bunch of points will be? It's a plane. If we have a linear equation, then fortunately, the graph of the thing, the plot of all the points that solve it, are a plane. So these 3 points determine a plane, but your lecture is not Rembrandt, and the art is going to be the weak point here. So I'm just going to draw a plane, right? There's a plane somewhere. That's my plane. That plane is all the points that solves this guy. Then what about this one? 2x minus y plus 0z. So z actually can be anything. Again, it's going to be another plane. Each row in a 3 by 3 problem gives us a plane in 3 dimensions. So this one is going to be some other plane. Maybe I'll try to draw it like this. And those two planes meet in a line. So if I have two equations, just the first two equations in 3 dimensions, those give me a line, the line where those two planes meet. And now the third guy is a third plane, and it goes somewhere. Okay, those 3 things meet in a point. Now, I don't know where that point is, frankly, but linear algebra will find it. The main point is that the 3 planes, because they're not parallel, they're not special, they do meet in one point, and that's the solution. But maybe you can see that this row picture is getting a little hard to see. The row picture was a cinch when we looked at two lines meeting. When we look at 3 planes meeting, it's not so clear, and in 4 dimensions, probably a little less clear. So, can I quit on the row picture? I'll quit on the row picture before I've successfully found the point where the 3 planes meet. All I really want to see is that the row picture consists of 3 planes, and if everything works right, 3 planes meet in one point, and that's the solution. Now, you can tell I prefer the column picture. Okay, so let me take the column picture. That's x times, so there were 2 x's in the first equation, minus 1 x's, and no x's in the third. It's just the first column of that. And how many y's are there? There's minus 1 in the first equation, 2 in the second, and maybe minus 3 in the third. Just the second column of my matrix. And z times no z's, minus 1 z's, and 4 z's. And it's those 3 columns, right, that I have to combine to produce the right-hand side, which is 0, minus 1, 4. Okay. So what have we got on this left-hand side? A linear combination. It's a linear combination now of 3 vectors, and they happen to be, each one is a 3-dimensional vector. So we want to know what combination of those 3 vectors produces that one. Shall I try to draw the column picture then? So since these vectors have 3 components, so it's some multiple. Let me draw in the first column as before. So x is 2 and y is minus 1. Maybe there's the first column. The second column has maybe a minus 1 and a 2 in the y's and minus 3's, somewhere there possibly, column 2. And the third column has no 0, minus 1, 4. So how shall I draw that? So nothing in this was the first component. The second component was a minus 1, maybe up here. That's column 3. That's the column 0, minus 1, and 4. This guy. So again, what's my problem? What this equation is asking me to do is to combine these 3 vectors with the right combination to produce this one. Well, you can see what the right combination is, because in this special problem, specially chosen by the lecturer, that right-hand side that I'm trying to get is actually one of these columns. So I know how to get that one. So what's the solution? What combination will work? I just want one of these and none of these. So x should be 0, y should be 0, and z should be 1. That's the combination. None of that. One of those is obviously the right one. So this column 3 is actually the same as B in this particular problem. I made it work that way just so we would get an answer, 0, 0, 1. So somehow that's the point where those 3 planes met, and I couldn't see it before. Of course, I won't always be able to see it from the column picture either. It's the next lecture, actually, which is about elimination, which is the systematic way that everybody, every bit of software, too, production, large-scale software would solve the equations. So the lecture that's coming up, if I was to add that to the syllabus, will be about how to find x, y, z in all cases. Can I just think again, though, about the big picture? By the big picture, I mean, let's keep this same matrix on the left, but imagine that we have a different right-hand side. Oh, let me take a different right-hand side. So I'll change that right-hand side to something that actually is also pretty special. Let me change it to, suppose if I add those first 2 columns, that would give me a 1 and a 1 and a minus 3. There's a very special right-hand side. I just cooked it up by adding this one to this one. Now, what's the solution with this new right-hand side? The solution with this new right-hand side is clear. Now I took one of these, and none of those. So actually it just changed around to this when I took this new right-hand side. Okay. So in the row picture, I have 3 different planes, three new planes meeting now at this point. In the column picture, I have the same 3 columns, but now I'm combining them to produce this guy. And it turned out that column 1 plus column 2, which would be somewhere there is the right column. One of this and one of this would give me the new B. Okay, so that's like we squeezed in an extra example. But now think about all B's, all right-hand sides. Can I solve these equations for every right-hand side? Can I ask that question? So that's the algebra question. Can I solve AX equal B for every B? Let me write that down. Can I solve AX equal B for every right-hand side B? I mean, is there a solution? And then, if there is, elimination will give me a way to find it. I really wanted to ask, is there a solution for every right-hand side? So now, can I put that in different words? In this linear combination words? So in linear combination words, do the linear combinations of the columns fill 3-dimensional space? Every B means all the B's in 3-dimensional space. So do you see that I'm just asking the same question in different words? Solving AX, oh, that's very important. A times X, when I multiply a matrix by a vector, I get a combination of the columns. I'll write that down in a moment. So that, you see, but in my column picture, that's really what I'm doing. I'm taking linear combinations of these 3 columns, and I'm trying to find B. And actually, the answer for this matrix will be yes. For this matrix, for this matrix A. For these columns, the answer is yes. This matrix is, this matrix that I chose for an example is a good matrix, a non-singular matrix, an invertible matrix. So those will be the matrices that we like best. There could be other, and we will see other matrices, where the answer becomes no. Oh, actually, you can see when it would become no. When could, what could go wrong? How could it go wrong that out of 3 columns and all their combinations, when would I not be able to produce some B off here? When could it go wrong? Do you see that the combinations, let me say when it goes wrong. If these 3 columns all lie in the same plane, then their combinations will lie in that same plane. So then we're in trouble. If the 3 columns of my matrix, if those 3 vectors happen to lie in the same plane, for example, if column 3 is just the sum of column 1 and column 2, I would be in trouble. That would be a matrix A where the answer would be no. Because the combinations, if column 3 is in the same plane as column 1 and 2, I don't get anything new from that. All the combinations are in the plane, and the only right-hand sides B that I could get would be the ones in that plane. So I could solve it for some right-hand sides when B is in the plane, but most right-hand sides would be out of the plane and unreachable. So that would be a singular case. The matrix would be not invertible. There would not be a solution for every B. The answer would become no for that. Okay. I don't know. Shall we take just a little shot at thinking about 9 dimensions? Imagine that we have vectors with 9 components. Well, it's going to be hard to visualize those. I don't pretend to do it. But somehow, pretend you do. Pretend we have, if this was 9 equations in 9 unknowns, then we would have 9 columns, and each one would be a vector in 9-dimensional space, and we would be looking at their linear combinations. So we'd be having the linear combinations of 9 vectors in 9-dimensional space, and we would be trying to find the combination that hit the correct right-hand side B. And we might also ask the question, can we always do it? Can we get every right-hand side B? And certainly it will depend on those 9 columns. Sometimes the answer will be yes. If I picked a random matrix, it would be yes, actually. If I used MATLAB and just used the random command, picked out a 9-by-9 matrix, I guarantee it would be good. It would be non-singular. It would be invertible, all beautiful. But if I choose those columns so that they're not independent, so that the 9th column is the same as the 8th column, then it contributes nothing new, and there would be right-hand sides B that I couldn't get. Can you sort of think about 9 vectors in 9-dimensional space and take their combinations? That's really the central thought that you get kind of used to in linear algebra. Even though you can't really visualize it, you sort of think you can after a while. Those 9 columns and all their combinations may very well fill out the whole 9-dimensional space. But if the 9th column happened to be the same as the 8th column and gave nothing new, then probably what it would fill out would be, hesitate even to say this. It would be a sort of plane, an 8-dimensional plane inside 9-dimensional space. And it's those 8-dimensional planes inside 9-dimensional space that we have to work with eventually. For now, let's stay with the nice case where the matrices work. We can get every right-hand side B, and here we see how to do it with columns. Okay, there was one step that which I realized I was saying in words that I now want to write in letters, because I'm coming back to the matrix form of the equation. So let me write it here. The matrix form of my equation, of my system, is some matrix A times some vector X equals some right-hand side B. Okay. So this is a multiplication, A times X, matrix times vector. And I just want to say, how do you multiply a matrix by a vector? Okay, so I'm just going to create a matrix. Let me take 2, 5, 1, 3. And let me take a vector, X to be, say, 1 and 2. How do I multiply a matrix by a vector? And just think a little bit about matrix notation and how to do that multiplication. So let me say how I multiply a matrix by a vector. Actually, there are 2 ways to do it. Let me tell you my favorite way. It's columns again. It's a column at a time. For me, this matrix multiplication says I take 1 of that column and 2 of that column and add. So this is, the way I would think of it, is 1 of the first column and 2 of the second column, and let's just see what we get. So in the first component, I'm getting a 2 and a 10. I'm getting a 12 there. In the second component, I'm getting a 1 and a 6. I'm getting a 7. So that matrix times that vector is 12, 7. Now, you could do that another way. You could do it a row at a time. You could do, and you would get this 12, and actually I pretty much did it here, this way. I could take that row times my vector. This is all the time, this is the idea of a dot product. This vector times this vector. 2 times 1 plus 5 times 2 is the 12. This vector times this vector. 1 times 1 plus 3 times 2 is the 7. So I can do it by rows, and in each row times my x is what I'll later call a dot product. But I also like to see it by columns. I see this as a linear combination of the columns. So here's my point. A times x is a combination of the columns of A. That's how I hope you'll think of A times x when we need it. Right now, we've got, with small ones, we can always do it in different ways, but later, think of it that way. Okay, so that's the picture for a 2x2 system. And if the right-hand side B happened to be 12, 7, then, of course, the correct solution would be 1, 2. Okay, so let me come back next time to a systematic way using elimination to find the solution, if there is one, to a system of any size, and find out, if elimination fails, find out when there isn't a solution. Okay, thanks.